Okay. I'm going to show a little bit about how I typically would approach an amplifier I just got that I don't know anything about. Of course I know about this one. I know it's working. So not likely to pick up any faults. So it could happen. It's not very likely. All of the tubes have been pulled out of it. They're sitting over yonder. The thing I've done so far for this test is I pulled the line fuse out just because it was convenient, a convenient place to interrupt the power supply to it from the line. And in place of this fuse, what is this thing? I think 3 ampere fuse, something like that. I can't see. Yeah, 3 amp fast blow fuse. So that's been pulled, and across where this was is this bulb, this lamp. It's a 60 watt, regular 60 watt light bulb. That will be, it serves as a current limiter, or a power limiter if you like. Certainly will do both. You could use a 40, you could use a 100. I just happen to have this 60 watt handy, so that's what I'm using. I have a more permanent setup in my lab elsewhere, but here we're just going to do it the relatively safe way with an old porcelain socket. So this lamp is across where the fuse would be, and it serves two purposes actually. It will certainly limit power, limit current, but it also serves as a sort of an indicator. If I'm doing something, I suddenly see that thing come full on, I know something went wrong. There's a reason somewhere that it's drawing a lot more current than it had been. So it does serve a dual purpose. So anyway, all the tubes removed. That because almost all of the high voltage, well actually all of the high voltage on this thing, it is produced through a 5U4 rectifier tube. None of that's going to be there. There will be no high voltage on these electrolytic power supply capacitors. However, there is a supply in here that's separate and independent from that which is fed from the 5U4 rectifier tube, and that's this little bit down here. These two capacitors, a couple of resistors, and this selenium rectifier. That is the minus 45 or 40 volts supply for the grids, the grid bias for the output tubes, which of course I just mentioned they're not in right now. So this power supply will come up and operate even without any tubes in it. That's the first thing. I want to make sure that the grid bias for the output tubes is at least reasonably correct. I know already that it's supposed to be 40 volts at normal operating line voltage. Now, the line voltage here, we're a little close to the power distribution substation. It's within eyesight, going out front and looking. So we get high voltage here. When I say high, I mean above 125 volts usually, under normal load conditions. Now, it being very, very cold out today, and there's going to be more of a load on it. Everybody's heater's working. It would tend to be a little bit on the lower side than it normally is. I've seen 130 volts here, our line voltage. So, bird flipping out over here. Anyway, so first thing, I've got a variac here to bring up the voltage slowly for another test we'll do. Just to give an idea, right now this is turned off. I'll set my meter here to read AC volts, auto ranging, so I don't have to worry about that. Turn the variac on, and put it all the way up. Okay, 126 volts on the nose. Not bad. But boy, we go through the light bulbs here. It's amazing how much you have to derate them just for 5 volts of difference, line voltage. But anyway, so that's the line voltage. This is right now connected directly across the outlet of the Variac. So I'll turn him off, turn him down, and move these leads to measure the negative grid bias voltage for the output tubes. Let's see, we'll just go to chassis. Chassis is ground here. And the output from this little power supply is right here. If you can see it, there's a white lead here that goes right over to these 2 tubes and is connected to the grids through a 68k ohm resistor on each one. Okay, so with full power I would expect to see 40 volts at that, give or take a volt or so. Power on. Oops, actually helped turn the amplifier on. And crank the voltage up. Now I'm just going to go to full Monty. Oh, we're on AC. Sorry about that. DC volts is what we're looking for. Okay, minus 41 volts. That's about right. Also notice that there's no glow from this lamp. Virtually no current being drawn from this at all, just that which it takes to magnetize the power transformer, which is obviously precious little. Now I could short out the secondaries of that transformer and not much would happen, but the light would come on. I'm not going to demonstrate it. It's not worth the trouble. A little dangerous, safety, health-wise, so not going to do it. So anyway, dang old birds outside. What the heck? Making my cats go nuts. So that's that. It's the bias voltage looks good as a DC. I'll go back to AC volts again and have a look. What's the ripple look like? I would expect it to be very, 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 very low because there's zero load on it. And with all of the tubes in and operating, even there, the load on it with no signal throughput is similar to this. 5.8 millivolts of ripple. That's like nothing. I certainly would not worry about that. Again, that only is associated with the output tubes, the grids of the output tubes. Yeah, you don't want to have ripple on those, but the amount of current drawn from this supply, even in operation, is so small. If these capacitors are even 1/3 of their rated capacitance, you never know the difference. A lot of folks, they see these selenium rectifiers and they cringe. I kind of do too. If they're in the main B+ power supply, or if there's current flowing through it and it gets hot. I've never had any trouble with these. Yeah, you could always just isolate it and put a silicon diode in its place. Even a germanium would work in this case, but if it's there, it's working, I'm going to leave it alone. The problem develops later down the line, I can certainly get at it and I know where to look. So there's that. The next thing, how do the main B+ supply filter capacitors look? And I already know, again, that these are in fine shape. And I went through and checked it out the same way. I'll go through it again, just so somebody else is doing this and never done it, knows a little bit about what to expect. So I'm going to turn the Variac all the way down, turn the Variac off, turn him off, he's off, and reposition. Now I'm going to stick on the chassis here. That's the valid ground for this unit. And I'm going to go to the first filter capacitor that's coming right off of the rectifier tube. Now that's the first one, and then there's dividing resistors on down the line, so you get progressively lower and lower DC voltages that are distributed throughout various various stages of tubage. What I'm interested, though, primarily at first is right up front, the first filter capacitor that's connected directly to the rectifier, no dropping resistors or anything. Now, you can do this with just a rectifier tube plugged in. One of these guys. This 5U4, or this one I happen to know is a strong one. I've got a bunch of these. Let's see. Another lovely example of that. I got a bunch of them here in various states of usefulness. Get into that later, probably the next vid for this, once I set her up and do some power measurements and tests and things. So you could do this test with one of these plugged in. The trouble with it is, until you get to a certain voltage, the heaters in here, which by the way in these 5U4 rectifiers, they're directly heated cathodes. Not that that matters a whole lot here, but until you get up to a certain line voltage level, these heaters won't emit, they won't have enough emissions to really get a stable control over the DC output from the tube. It's almost like you get to a point and then bang, you got all this voltage on the electrolytics here. It also can be a little bit more confusing if you're trying to use this as an indicator as what's going on with the thing. So what I do is put in place of this, or something like it, depending on what I'm working on, but it's basically the same. It's just, it's an old broken tube socket into which I put some rectifier diodes, and in this case also added a indicator. This is just a 5-volt light bulb incandescent lamp connected across where the filaments here would go. There's some details about this I don't want to get into here that are important to know. If you're doing this and you are wondering which side of the heater cathode to put the diodes to, it's the one that goes to pin 8 normally, but don't bet your life on it. It might be wanting to go to pin 2. The heater on the heater cathode on these goes between pin 2 and 8, and it doesn't matter a whole lot with the tube because the resistance of these heaters is very low compared to the voltages that the B+ uses. So it really doesn't matter a whole lot whether the common to the two diodes, that being the heater filament, it doesn't really matter whether the instrument takes it from pin 2 or pin 8. This has been wired as is the common way to deliver that full Monty to pin 8. So in other words, the B+ voltage does not pass through the heater. This will indicate if it is, because it will get brighter when you start drawing current, when the amplifier starts drawing current. That won't happen here because this lamp is completely independent. So it's got its own little 5-volt supply, which is only meant for the heater cathodes and the rectifier tube. And this gives you, because it's solid state, as soon as I bring up the variac, current will flow through this rectifier and into the capacitors, and I'll be able to see it on this meter and gauge how much current's being drawn here and get an idea where these capacitors are. I'll certainly demonstrate this. With this unit, there is, because of this power supply, even though it doesn't have any other tubes in it but the rectifier, there is a current drain on it, and it has to do with this power supply bit that raises the heaters of all the other tubes. It puts a DC bias on them above ground. about 18, 20 volts above ground. And they derived that, it's a positive voltage, and they derived that voltage from the 480 volts rectified B plus voltage. So that circuit draws quite a bit of juice. So there's going to be some current draw just because of that. Without that circuit, what would happen is if I brought the power up, this would glow for a bit, the capacitors would charge, it would extinguish, hopefully, and that would be an indication that, well, there's not excessive current flowing through or into the capacitors anymore. But with this power supply in there, like it is, there is going to be a load on it, even if the capacitors are fine. So that's going to makes it a little bit tricky if you don't know that this power supply is there, or that this heater bias supply is present. If you're not aware of that, it can be confusing. You say, well, those capacitors are very, very leaky because I got all this current flowing where it shouldn't be. No, in here it's going to be some current flow. What I'm primarily going to be interested in is excessive current flow, and I want to know what the voltage is across these capacitors. You'd be able to tell the difference. You could put a jumper clip lead directly across one of the capacitors, and you will see the current go way up, indicated by an increase here. You could put a meter there and measure it, but the distinct advantage of this is it's not just an indicator. Of course, it's also a limiter. It's not going to draw more than 60 watts. In fact, in all cases, it'll draw somewhat less than that. The bulb by itself will draw 50 watts, but with the amplifier here in series with it, no matter what you do, you're never going to get beyond that. So I'll plug this in to the rectifier socket, and variacs down and off. Turn the amp on. Again, we're measuring right now. We're just measuring the bias supply. So, since we've already done that, oh, I already moved the clip. Okay, we are in the right spot. Just double check, double check, double check. On ground, on the business side of this filter capacitor. Under normal operation, that sits with a vacuum tube rectifier in it. More on that later. That sits about 480 volts. Those are 500 volt capacitors. This one, and this one. Each one is a multi-section. This one, by the by, it's 2 sections, but they've just got the 2 sections parallel, so it's essentially one capacitor right there in circuit. So go ahead and switch on the variac. Make sure we're looking for DC volts. Variac's all the way down, so we got nothing. So I'm going to go up to 10. Which, of course, this power supply transformer being a step up, it's yielding 40 volts across this right now. And I'll let that sit for a moment. See if it moves. You know, if I see this start to go down, off the power goes, and we dig a little deeper. But, you know, at 40 volts it seems just fine. It's going to move around a little bit because it's unregulated line voltage going into the thing. You got no light, so not drawing much current. So we'll take it up to 20. Now these numbers I'm saying take it up to, they're approximate. If I dial this up, the highest dial, the high end is, it says 120. Well, that's assuming 120 volts in. It's actually 126. So these numbers are approximate. So I'm dialing in 20, so it's a little higher than 20 volts going in. I wouldn't expect to see much there under any circumstances at 20 volts going through it. And that's leaving 90 volts across this cap. Now, I'll take it up. Now, I'm not watching the dial so much as I'm watching the meter. Let's take it up to about 120 volts. and see what it does. Sort of settled in, moving around a little bit. That's what you'd expect. A couple hundred millivolts. Okay, so and I'm not seeing any problems now. If the capacitor's open, we wouldn't see much happening at this point anyway. If the capacitor's shorted, you'd see a lower voltage here at this point. So let's poke around a little bit further down the stream. See, the next place it goes is there. Okay, that looks about right. There shouldn't be any load on these capacitors. The only load really is up on the front end because of this lifting circuit for the heaters, tube heaters. So 100 volts on there should be 100 so volts on there. All the way down the line, that looks good. If any of these capacitors had a problem with these dropping resistors, you'd see a drop in voltage, and there's none. So it doesn't appear that any of these capacitor sections are a problem. At least at 100 and some volts, 102 volts. So we go back over here. Now you see the little bit of a drop there, or difference, 122 here, and all the rest of these it's 102. Well, that's because this section is removed from this load, this heater lifting power supply. Oh, which, by the way, let's have a look at that, which is now at about 5 volts. Yeah, so that's actually the where they tap off for this heater lifter is from the screen grid supply. The screen grids for the output tubes, their supply. And I know it seems a bit cavalier me poking around in here with my fingers like that, but we're gonna not do that so much, because I'm gonna start get some high voltage in here. Let's take this up to 200 volts. And while you do this, keep an eye if you see your lamp start to glow and the voltage quits rising as you increase your voltage you might have a trouble. Now, I've already gone through it. I know what to expect. I could go through and again measure all of these. I'm not going to bother to go through that. You saw what I did. But if this were truly a fresh amplifier I've never been in or worked on, or even looked under the hood, I certainly would, as I go through each change, upward in power supply voltage, I would go through and do a check, because there may be a voltage level at which one of these capacitors could begin to leak or fail. And one way to know that is, or notice it, is to just keep a constant look at them through these dividing resistors. If it starts getting lower and lower and lower as you go through, and there are no loads on it, you might have trouble. And also, if this begins to glow. So yeah, let it sit like that for a while. I'm going to expedite matters because of the video. Take it up to 300 volts. Let that sit for a while. And that's with the voltage input, the AC line voltage input is just about 85 volts so far. Now I am going to pull it all the way up to the full line voltage. At that point I would expect to see, because of this power drain for this heater lifting power supply here, I would expect to see some light from this ballast bulb. So it's not moving around there anymore, so we'll go ahead, put it up to 400 volts. Or thereabouts. Okay. Maybe difficult to see because I've got 600 watts of stage light over there. But this is indeed beginning to glow a little bit. Not surprised at all. In fact, I'd be surprised if it didn't. Let me see if you switch. I'll switch the variac on and off, see if you can notice. Oh, it's awful dim. There's also, I've turned it off, the power, or the variac's turned off. You might see it surge as it charges these capacitors and these capacitors. Right? Probably should have been able to see that. So, I'm all the way up, 126 volts going in, and that's all we're going to get, 407 volts. That's being limited by this ballast. Of course, when he heats up, his resistance increases and it increases the voltage drop across it. So the AC voltage going into the line of this, the line input of this amplifier is not 126 volts because of this lamp. It won't be until I put the fuse back in, and I'll tell you, when that happens, the voltage with that solid state rectifier in there, the voltage across these capacitors actually gets higher than their rated value, which is 500 volts. I think last I looked, I saw something like 525 volts, and that was under load, all the tubes in it. So anyway, if there were a big trouble with this, with the capacitors, you'd see some activity with that. Getting brighter, maybe getting dimmer, or just, it should not move around in brightness, if at all. And this voltage should stay, within a volt or so, assuming you got a fairly good line voltage, live in the middle of New York or something. So let it sit that way for a while. I'd go an hour, just to be sure, and check temperatures, and turn everything off, discharge everything, and check the temperatures of the capacitors. They should not be warm. If they're warm, something might not be right. They might be leaking. You see changes in the, if this suddenly comes on or it seems different brightness, you might have a problem with the capacitors. It's a good idea to bring them up slowly, slower than I did here for this demonstration. Be patient and watch what you're doing. Keep your fingers out of it. If you don't have a variac, you can just use a ballast lamp in series with the line. It can work for you, but if you're going to do that, I suggest start off with a very, very low wattage lamp, maybe even a 7-watt lamp, like a night light, and work your way up from that. Go to 7, and then maybe a 25-watt bulb, and then maybe a 40, and then the 60, like that. If there's a major problem, it will prevent catastrophe doing it that way. It's convenient to have a variac, but you don't need it for this. You're using a ballast anyway. Once I'm satisfied that everything's a-okay with it, I don't use the ballast at all anymore anyway. I don't even use the variac. I just go full Monty with them. And if something happens, they'll let you know. If something goes wrong, it'll let you know. And sometimes that's really the only way you're going to find out. So you start actually pumping some watts through the beast. So that's that. I'm going to cut this off, put the fuse back in, get rid of the ballast, put all the tubes back in and do some other function tests on it and see how that goes.